In this video, I wanted to talk a little bit about engineering, and one of the assignments I'm going to have you do is to read the first two chapters from the Oakes and Leon book. Hopefully you have this, or we'll have it soon. The first two chapters, when I thumb through here, they talk about, let's see, the heritage of engineering, sort of the history of how it's developed, and then different engineering majors. All right, so I wanted to use that as a lead-in and talk about, what you're about to embark on is engineering at Baylor. And so this is an excerpt for a presentation that I often make about recruiting at Baylor. This comes from an event that we call Premier. You may have actually seen part of this presentation, but it talks about the mission of Baylor, the mission of the School of Engineering and Computer Science, and then what is engineering. And it has lots of pictures involved, and I thought that'd be a good way to start this discussion. So here's the first slide. The first slide is Baylor's mission is to educate men and women for worldwide leadership and service by integrating academic excellence and Christian commitment within a caring community. So hopefully you'll continue to get a sense of that. We care a lot about the academics, but we also want to support you and make sure that you feel a part of this community. So that's part of what we're after from the very beginning, and so I wanted to put that out there. Okay, the next thing I wanted to talk about, get this slide to advance, is the School of Engineering and Computer Science mission. Okay, we get a little more specific. We want to educate students within a caring Christian environment. Of course, the Christian part is important. We want to combine a strong technical foundation with an emphasis on professional, moral, ethical, and leadership development. So these things don't happen in a vacuum. We care a lot about the technical side, so you're going to get a lot of problem-solving kind of things. You're going to get some instruction on how to derive formulas and how to think as an engineer, and hopefully you get some hands-on experience as well. But we don't just do that part. We also, you'll see, the first week's module, it has you involved with some team members. We're going to design this camera photo stand, and so you'll work with some people on ideas to make a better camera photo stand and hopefully start this process. Okay, so next, let's talk about, let's skip this slide and let's talk straight to what is engineering. And if you're not familiar with Gary Larson at Farside, you should be. Unfortunately, he retired several years ago, but he has a ton of great cartoons. Here's this one that I really like, Experiments in Early Transportation. And then you can actually make a good point with this one. Here's this cartoon of scientists, and they're saying, of course, we're not exactly rocket scientists. And that's an important thing because there's a difference between science and engineering. Okay, science has to do with, making a hypothesis and coming up with experiments to support that hypothesis or to prove that hypothesis wrong. We're more about applying some of the ideas you get from mathematics and science towards solving problems. Okay, so we're going to talk more about that now. Okay, so I made this slide for the Premier presentation, and my idea is to just simply list some things that have some component of engineering. Okay, so the very first thing I listed was, I thought big. What is the thing you think of would require just a ton of engineering? And the first thing I thought of was the space station, and that became even more relevant recently with the launch of the SpaceX capsule, the Dragon capsule that docked with the space station. So I updated the picture here, and we have a picture of this amazing event that sort of has revived our entry into manned space missions that they launched from the US. Okay, so obviously that requires a lot of engineering. So the very next thing on my list, I put the smallest thing I could think of. So I looked on my desk and there was a paper clip. And a long time ago I did this. I Googled designs for paper clips, and at the time there were like 17 patents that you could get for a paper clip. All right, so clearly there's some design work that goes into something simple like that. All right. And so then I thought, well, what are some mundane things in our life? And one thing is a refrigerator. A refrigerator is an excellent example of thermodynamics. If you're interested in mechanical engineering, you'll have to take that class, and you'll learn all about how the theory of that works, and you can apply it in practical applications. I know students are also interested in video games. Video games is part computer science, part computer engineering. There's even some mechanical engineering components on that, because a video game console, you know, there was problems with the early Xboxes where they would overheat because they didn't have the right thermodynamics solutions involved with keeping the heat out of the processors, and things would literally melt. Okay, so all kinds of problems with that, and things that you can do in that area. All right, the next thing on the list was artificial hip, because I know some people are interested in biomedical applications, and I wanted to think of, think of something that's biomedical. In an artificial hip, you have to come up with the right type of material that can go into a body and not be toxic, but yet it has to last a long time, because people don't want to keep having a surgery over and over. Okay. The next thing on my list is cell phones, because I'm a communications engineer, right? It's one of the areas that fascinates me the most. And so I think the development of the cell phones since the early 2000s to now has been remarkable. Okay, the last thing on my list is roads and bridges, because that's often the first thing that people think about when they think of engineering. Okay, and so roads and bridges, you'll read in the own text that that's more civil engineering. We don't do civil engineering here, but we'll explain more about the engineering types as you read through that textbook and we have our discussions. Okay, so next what I want to do is just simply show some pictures of things that you might not have thought of in terms of what it takes, engineering problems that can be applied in today's society. Okay, so the first thing I thought of was power and energy. And so you take a look here. This diagram is supposed to be illustrating the power grid in the United States. And of course, that's an important thing. Without the power grid, we don't have power, and society would not function properly. All right, so here's a picture of windmills. Think about windmills, right? There's a little generator on the windmill. The wind is blowing, it's spinning the generator, generating electricity. It has to connect to the grid. It's got to have some type of distribution system. So that's what this is showing here. And the thing about the wind is it's intermittent. On a windy day, you may not know this, but on a really windy day, Texas, which has a lot of windmills out in West Texas, if you're from West Texas, let me know about that, because I think these are fascinating to look at as you drive through West Texas. But on a windy day in Texas, up to 30% of Texas power comes from wind, right? So that's a challenge, because this energy has to connect into the grid, all right? And connecting green sources like solar and wind that are intermittent in nature presents challenges for the grid. Okay, so we have some professors here at Baylor that do a lot of work in this, and it's obviously an important field. Okay, you might think of this as electrical engineering because it's distributing electrical power, but this windmill design, that's mechanical. The actual blades and turbines, the shape of the blades, turning the electrical turbines, that's a big part of mechanical engineering. Okay, next on my list, control and aerospace and robotics. Okay, this is a blend You know, I like to tell students these engineering disciplines, sometimes it's artificial. These boundaries that we create are artificial. All right. If you're going to work in the aerospace industry, you need to know probably a little bit of mechanical engineering, a little bit of electrical, a little bit of systems engineering to put everything together. Okay. So I like this graphic because this shows you, this looks a lot like a MATLAB plot. Okay. We'll talk about MATLAB later, but this is showing you the math behind a little controller. All right. And a controller can be used to control the action of like a robot arm or the control surfaces on a jet airplane. All right, so you'll end up in your senior year taking a course where this kind of diagram will make some sense to you. All right. Okay, next on my list is RF and electromagnetics and optics. All right, let me move my picture here. This is a picture of a cell phone tower. And there's a lot going on with a cell phone tower. Of course, there's the structures involved. So the mechanical engineering folks have to design that to where it can handle these, you know, the wind loads and the storms that we get. And we don't want to have the towers falling down. But then with the electrical side, you're connecting antennas and coming up with the right antenna patterns to give you coverage for effective cell phone coverage and performance, right? The other thing I have showing in this picture is, you know, a lot of times what I hear from students is electrical engineering, I can't see it, you know, like I want to do mechanical because I can see it, I put my hands on it. And I'd make the argument that in a way, that's why electrical engineering is cool, because you're dealing with things that aren't as easy to work with because you can't see them. But yet we have tools that will let you imagine what's happening with, say, an electromagnetic wave. All right, so here's a picture of an antenna pattern. And we can do that and come up with solutions for things, you know, that ultimately end up in practical systems like cell phones. Okay. Then, of course, this is showing optics, all right, light has the capability of transmitting a lot of data very quickly. And so that's yet another area that electrical computer engineers can work in. And yet the materials involved are part mechanical and probably you could even argue it's part chemical engineering. All right, so a lot of diversity in the problems that you see in engineering. Okay, next. I've already talked about communication systems. You know, you get another slide if that's your area of interest. And of course, this is of interest to me. This upper graphic in particular is showing a network of satellites that can help land an airplane at an airport. Of course, we can do that with GPS systems. We know about cell phone systems and how sophisticated those have become. Okay. The next thing on my list, you know, this is just showing sort of the growth that we've seen in technology. And part of the point I want to make is that technology is always growing and changing and improving, right? What's not changing are the fundamental principles that let you develop the technology. So here's a picture of a really old computer that's probably much slower than the computer you have on your cell phone. Right, so inside your cell phone, you have little microprocessor chips that are much faster than this whole room full of old computers. All right, so that's how that works. You know, things just evolve over time. And because technology is growing, it requires engineers to be able to grow with it. All right, and it requires you to know a little bit more about other areas that you wouldn't necessarily have learned about in the past. Okay, so that's why we talk about you know, if you're a mechanical engineer, you need to know a little bit about electrical so you can continue to learn in that area. And if you're an electrical engineer, you need to know a little bit about mechanical engineering so that you can help solve problems that support the solutions in your industry. Okay. All right. Put this on here just see if you have thought about it. You know, one of the things that is going on these days is if you look at cars, there's all types of what we call embedded systems. This doesn't happen with just cars. Your microwave oven has, you know, an embedded microprocessor. We're seeing smart devices in the home. Even your light bulb has, you know, I've got a bunch of few light bulbs that have Wi-Fi receivers that let me control the lights from my phone. All right, so embedded system, there's engineering all over the place, and it's an interface between electrical and mechanical. You end up with a lot of electromechanical systems, motors and gears and things that help us make all these things work. Okay. All right. Let's see. Some of the things we work on the electrical engineering side, especially, have to do with using. I'm sorry. There we go. With using computers to process signals. Okay, so here's, you know, this is an old slide. This is a picture of Siri. You know, we have Alexa and Google Assist, and we know that voice recognition has become a part of our daily lives. But yet, if you think about it, it's still not great. It still doesn't work as well as we would like it to work. So it's going to continue to evolve. If you're interested in biomedical applications, here's a picture of you know, a brain imaging, and use a lot of signal processing to come up with effective imaging techniques that help in the medical profession. Okay, next, when you read the Engineer Your Future book by Oakes and Leone, they talk about a definition of engineering. And probably if you asked every engineer, you get a slightly different interpretation of what is the definition of engineering. And so, you know, it's important to know the breadth of opinions, all right? But my view, engineers turn ideas into useful systems or products. Okay, so that's a pretty simple definition. All right, so let's go with that one. And also, I'd like you to read what they say in the book about it. Okay, so where we're heading, it's important to know where you're heading so that you can make adjustments and plan on how to optimize your time at Baylor. This is sort of an input-output view of how you become an engineer. All right, so here are the courses: math, chemistry, physics, materials, you know, like electrical materials on the electrical side, how you make a transistor, for example. Then there's costs that are involved, and along the way you pick up a little bit of what we call engineering economics. It's important to be able to communicate your ideas, work with people, be able to use computers, because that's just the way things are done in engineering. Like I said, work with people, do the art of design. So obviously it's important for us to get you started early on design. That's why week 1, module 1, you're building something, right? And so we want to get you thinking in terms of the creative part of engineering. Okay, and then time, just like anything, as you progress through engineering curriculum, you're going to learn to manage your time. Otherwise, you won't be successful, all right? Because it is a lot of demands on your time to be successful in these more challenging majors. And that's going to be true in the workplace as well. And so as you go through school, all right, you become an engineer capable of producing products, systems, and services that people want and need. Okay, so it's an exciting time to be an engineer just because there's so many cool problems to work on and so many different industries out there. In fact, there's a good chance that by the time you graduate in 4 years, you'll take a job that doesn't even exist today. Okay, so that's where I'm going to wrap it up. You know, what does it take to become an engineer? Well, that's probably what you're in the class for. Hopefully you're curious about how things work. You like math. You like using computers. I'll give you a pass right here since chemistry. I'll give you a pass on chemistry. I wasn't a great fan of chemistry, but you know, if you like chemistry, that's all the better. Okay, and as I mentioned before, you don't do these things in a vacuum. You need to work on, you know, learn to work together as a team, and we'll get started with that right away as well. I know a lot of students come in, they're worried that they're behind. Maybe you didn't have a calculus class, maybe you didn't take an engineering class in high school, maybe you've never touched a computer and done some coding. Let me tell you, that's going to be okay. All right, we're going to start from the beginning, and you just have to kind of roll with it and learn it step by step, and I think you'll be fine. I know it creates some anxiety for you at the beginning, but we can work our way through that. Okay, so that wraps this one up, and we'll see you next time.